Today, we are privileged to have as our first guest speaker, Mr. Arun Murthy. Mr. Arun Murthy completed his master's in the field of combustion and propulsion in IIT Madras in 1985. He worked as an engineer in VSSE ISRO from 1985 to 1989. He has been with Fluidyne for the past 32 years. His fields of expertise include CFD, heat transfer, numerical methods, parallel solvers, atmospheric flows, MHD, etc. In this lecture, let's hear from him his experience and views on the subject of nuclear. Welcome, sir.
Good morning, everyone. Professor Vinay Kumar.
Yes, sir.
Actually, it will be my colleague, Dr. Anil Kumar, who will be presenting this session.
Okay, sir.
I will be the speaker for the next session on pipes and fuses.
Okay, sir. Sure, sir.
Dr. Anil Kumar is there. He has worked extensively on the nuclear applications, especially on the multi-phase flow side, because nuclear applications are heavily populated with multi-phase flows. And he has a very good experience on those things. So I would request Dr. Anil Kumar to present, to speak in this session.
Okay. Welcome, Sir Anil Kumar, sir, for this session. Please go ahead and start your session, please.
Good morning, everyone. Thank you, Dr. Yadu Krishnan. Okay, let me share the shall we start?
Yes, sir. Go ahead.
Fine. So once again, welcome, everyone. Today we will see some of the case studies we have done in the recent past, in the past 10 years, and we are continuing some of the studies we are continuing to do in the area of nuclear engineering. A nuclear power plant from outside, it looks like this. It has the prominent feature that is visible in many nuclear plants, not everywhere, is a cooling tower. Then there is a reactor building, which normally with a hemispherical dome. Typically, these reactor buildings can have multiple levels under the ground, 7 or 8, depending on the design and other features. Normally, these are situated near water bodies. So if you look at the statistics on that, India has significant proportion of nuclear energy in its energy production. In addition to the power generation, the nuclear technologies are applied in various other fields like medical or food irradiation or in carbon dating and propulsion systems for submarines. And as all of you are familiar that we are now, India is trying to build or has already built a nuclear submarine, and so going to build more of these. Actually, these will also be used in space propulsion. A nuclear power plant, the core of a nuclear power plant is its reactor, which converts the nuclear energy into thermal energy. The fuel rods which releases this energy are surrounded by a coolant, not normally we use a heavy water, or normal water, but we call it PHW or PHR. And this heated water is taken to a steam generator. Normally, these water which receives heat energy from the fuel rods, these are at very high pressures. But there are also so that it doesn't boil, so it remains at very high temperature in the liquid state. But there are a few boiling water reactors also. So this heated water is taken to a steam generator where it heats another circuit of water, generates steam, which is passed to steam turbines and generates electricity. And the residual heat is taken out of the system to cooling tower or into a reservoir. Yesterday, we saw one example of steam turbine, some application of CFE, a multi-phase flow through a steam turbine to help in the design of water trucks. So this is the nuclear power plant is one area where steam turbines are used, and actually that turbine which I was talking yesterday was actually being built to be used in nuclear reactors. So a nuclear power plant has various equipments. It has a reactor pressure vessel and steam generator. Then there are pumps, electromagnetic pumps in some cases, then turbines, condensers, cooling towers, and so on. And a lot of piping and containment structures to protect the outside environment from any possible leakages. If you look at the processes typically occur in nuclear plants, and where we had applied computational fluid dynamics to analyze the designs or to analyze the operating conditions or to compute the consequences in case of an accident. You can see that there are many things like neutronics, that is transport of neutrons and their absorption, subsequent heating of surrounding liquid metal circuits, fuel rod cooling, and thermal hydraulics, that is heat transfer and multi-phase flow, vortex-induced vibration of pipelines, ruptures or leaks, radioactive leak and transport of radioactive nuclei. And another important aspect process that may occur or which is studied extensively is the hydrogen leak into the containments and their dispersion, and possible subsequent explosion. And normally, and also this nuclear power plants, various components, almost all components, including the structural components such as even doors, are studied for safety and robustness in case of seismic activities, like earthquakes. We had seen 10 years back, there was an earthquake and tsunami which affected the Fukushima power plant. So these plants, each of the components are normally designed to very high standards of safety. So to summarize all these processes that we had seen, multi-phase flow, chemical nuclear reactions, heat transfer, fluid structure interactions occur in various regions of nuclear power plants. So we have worked extensively on thermal hydraulics or steam water hydrogen systems, hydrogen dispersion, explosion, and mitigation, nuclear buildings, ventilation, waste management. That is another aspect. We will see one example about which we will see one example. And radioactive dispersion in buildings and in the surrounding atmosphere. We have used all the methods that we had seen yesterday in these analyses. Any of these methods were developed and validated for specific uses in the nuclear industry. Some of them include, for example, homogeneous equilibrium model and multi-fluid Eulerian models, etc. So let us see, we will see some of the case studies we have done. Normally, when we develop a tool, a simulation tool has to be used in an application related to nuclear power plants or nuclear industry. Very strict, it has to go through a very strict validation process. And there are many experimental programs, which conduct a lot of experiments and collect a lot of data. One reason is once a reactor is built and starts operational, it is difficult to collect data and conduct experiments on them, on various issues. So to collect data required for design and further analysis, experiments are set up, test benches are set up, which have, and similar situations that occur in a reactor are reproduced. And these data are many of these data are widely available in the public literature. So if anyone who wants to develop a simulation tool or use a simulation tool for analyzing the processes in nuclear industry, first we may have to go through an evaluation process where one of these problems are taken and the results are reproduced. One such program is called THI, Thermal Hydraulics, Hydrogen, Aerosols, and Iodine Experiments. You can find the details in the OECD NEA website. THI program basically consists of a cylindrical vessel with a volume of 60 meter cube. And it has many facilities to perform various types of experiments, like injecting steam into the vessel, steam or liquid water into the vessel, and also injecting hydrogen at various levels, or conducting explosion experiments, and so on. So in one of the case studies, when we started developing the developing certain models for the thermal hydraulic analysis of reactor fluids, we had done simulation of one of the problems. So this involved the injection of steam and hydrogen, a mixture of steam and hydrogen into the vessel. So the steam enters the vessel and it condenses, forming liquid droplets. At the same time, it increases the pressure. So the objective of the study was to see the distribution of hydrogen concentration and its stratification. Why the purpose of this study is to see how the hydrogen behaves in a condensing environment. The hydrogen is a very light gas, so as it comes out in an open environment, it goes up due to buoyancy. But in a containment, it may go to the top and may mix with the surrounding air and form a reactive mixture. if there are any pockets of this reactive mixture which are within the limits of flammability limits, it can cause explosion and failure of the vessel. Flammability limit means there is a certain limit. For example, if the hydrogen volume fraction is between, say, 4%, 75%, it can get ignited. There is a lower limit and an upper limit. So the ventilation systems, the vessel design, etc., should be such that even in case of an accidental release of hydrogen, it should not form a reactive mixture within the flammability limit. So this a lot of this experimental data on hydrogen concentration at different locations are available for this experiment. So this was one of the first studies we had done to validate our homogeneous equilibrium model. So these considered steam injection, steam evaporation, and condensation, formation of valve film. The actual simulation time was about more than 1 hour, because these process may have a bit long, it takes place for a long period. And so you can see here on the left-hand side, you can see the hydrogen concentration. There is not much hydrogen at the bottom. It goes and gets stratified at the top. So initially, the vessel was full of air. Similarly, you can see that at the steam injection point, liquid water is formed due to condensation of steam, but the liquid volume fractions are very low. So that also goes along with the natural convection. The steam also gets stratified because steam molecular weight is also less than the air, and also it is at a higher temperature. And the values of various things like temperature, hydrogen concentration at different points are compared with the experiments. And before finalizing the suitable models to analyze actual problems, various parameters and models like turbulence models are tested, and most suitable models are selected based on this experiment. Then they are used in the actual situations. Similar to TAL, there is another experimental program setup, which is called the PANDA. In TAL, there was only one vessel, whereas in PANDA, there are two interconnected vessels. These are called dry wells. The idea behind is that in many plants there are different containments which are connected through passages or other pipings. So in case something happens in one of the areas, how these materials will be transported to the other place, and how much of it will be transported. And these connections and vessels should be designed such that the domino effect, chances of domino effects are minimized. So these vessels are of volume of 90 meter cube. These are fairly representative of actual vessels, though at a smaller scale. In this particular study, the objective was to analyze the distribution of helium. Helium is used in lieu of hydrogen in many times because helium is lighter compared to air, and it is also non-condensing. It also doesn't condense. So helium is used in this study. The physical process are similar. Here, sorry, the helium is injected on the left in the left vessel, And as you can see, since the helium is a light, goes up and gets stratified at the top, but eventually, as the another aspect of hydrogen and helium, which are smaller molecules, that their diffusivities are very high. So when you do simulations with these gases, we cannot assume constant diffusivity. We cannot take its diffusivity as that of heavier gases. We have to take the appropriate value of the diffusivity. So the diffuses, and we can see that after some time, say after 2000 seconds, the helium goes into the other vessel and again gets stratified at the top. So there is no helium at the bottom part of the vessel. So we can also see that the steam concentration on the bottom right corner, the steam is also injected along with helium. So we can see that at the inlet, the red color patch of steam, it indicates larger or higher mass fraction of steam. But since the ambient temperature in the vessel is lower, the steam condenses. So we can see that at the top right picture, the water, the water mass fraction. So there is no water at the point of injection, but as it disperses, as the steam disperses and gets cooled, it gets condensed. So this simulation was also done using homogeneous equilibrium model with buoyancy effects and gravity effects. And the results were compared against the available experimental data. Again, similar to the earlier case, various parametric studies were conducted to arrive at proper models and model parameters. When we talk about the nuclear industry, there is another kind of reactor. Many countries are working on nuclear fusion reactors. One of the important organizations working in this is called ATAL, International Thermonuclear Experimental Reactor. You can go to their website. In these reactors, in the earlier reactor, the previous one, nuclear fission is used, whereas in this case, the nuclear fusion is used to generate energy. This reactor normally contains a vacuum vessel. It contains plasma at very high temperatures. It's actually a replica of sun. So the temperatures are very high and the pressures are very low. It's near vacuum. The energy is produced in this vacuum, the core in this vessel, and then this energy is taken out again by high pressure liquid water, which are circulating in what is called a blanket, a shield module. And these are huge facilities, and these walls are made of panels and various passages through that. So one important aspect of its operation is that this plasma can exist on very low vacuum levels, like 10⁻⁶ pascals. It's at molecular level. Any disturbance of this vacuum will quench the plasma, and the operations will have to be stopped. So even a micro crack, that is cracks of the size of micrometers, can cause leakage of very small amounts of water or steam, that is cooling liquid, into the plasma. So what is being done is one idea. It's around about 10 years back. These designers thought was to put sensors of molecules at very low concentrations of these things Then as soon as the presence of any small amount of foreign molecules are found in the vacuum vessel, its source can be located. So for that, to decide that transducers or to the sensors, it is essential to know the possible concentrations that can be caused by the possible leaks. So again, it's difficult to do experiments. It's very expensive to do experiments. It's also time consuming. So this process was done through simulations. So we participated in this, and we have done this project. The part of this involved the vapor plume development in the vacuum vessel due to the leak of high pressure water and high temperature into this. So you can see small pictures of this. The pressure, the minimum pressure goes to 10⁻⁴ Pascal. So we can see that if you the difficulty here is that the flow through the pipes or the blanket shield module passages, these are highly at high pressure and high temperature, and there are very small passages like micron sized passages, and in the vacuum vessel there is near vacuum. So the one difficulty here is that in some part the flow is in continuum regime, but in other parts the flow is in a rarefied regime. So the Navier-Stokes equations that are derived, it is not valid in this. The continuum framework is not valid in this regime. So normally these regimes are identified based on the Knudsen number Kn, which is the ratio of molecular mean free path to the flow length scale. The molecular mean free path, as all of you know, is the an average distance traveled by molecules before between subsequent collisions, and flow length scale is the characteristic size of the flow domain. For example, diameter of a pipe or width of a crack, size of a room, and so on. So this, as Knudsen number is, if Knudsen number is large, or if it is much more than 1, then it is called a free molecular regime. Here, the intermolecular collisions cannot be neglected. Normally, this occurs in outer space. So, any simulations to be done with respect to satellites, we have to consider these rarefied flows. The same thing happens in vacuum vessels. When Knudsen number is much less than 1, the gas or the fluid can be considered as a continuous medium. And there could be regimes in between. So there are different methods developed to apply in different regimes. For example, when Knudsen number is less than 0.01, the Navier-Stokes or equations can be used. As the Knudsen number increases slightly, the Navier-Stokes equations can be modified with some velocity slip conditions or temperature jump conditions, because the no slip conditions will no longer be valid, because there are not sufficient number of molecules to make that, to assume that the velocity, there is a continuity in the velocity or the temperature between the wall, between the structure and the fluid. And as the Knudsen number increases further. Certain other methods are developed, and we had to go to a solution of Boltzmann equation or direct simulation Monte Carlo techniques. In the present study, which I had mentioned, we used a combination of Navier-Stokes solvers with velocity slip to model the flow in the upstream of the leak and through the leaks, and used DSMC, direct simulation Monte Carlo technique, in the vessel, in the vacuum vessel itself. You can see the details of this work in the paper published and presented. And this slide shows some of the results obtained. The right-hand picture shows the simplified the schematic of the problem domain. On the left side domain, condensed water at high pressure, and there is a thin gap or depth. The size is about microns, and at the end the pressure is very low. So as the water, high pressure water, passes through this passage, the pressure drops. As the pressure drops, it evaporates. So you can see that pressure plot. The x-axis is distance from the inlet of the channel, micro channel, and the y-axis is the pressure. So you can see that pressure is decreasing from inlet continuously at a slower rate, and in this region it is still the liquid. There is not much of there is no evaporation, but as soon as the evaporation takes place, it gets converted into steam, and the volume flow rate increases, so the pressure drop also increases suddenly. You can see the vapor volume fraction also follows a similar pattern. At around 1 millimeter from the inlet, or 2 millimeters from the inlet, there is suddenly evaporation, and the steam volume fraction goes to 1. So we can see that the evaporation takes place in a very small length of 1/10 of a millimeter. So the methods that used should capture this highly transient phenomena. The velocity variation also shows corresponding increase, sudden increase. Here, the velocity is very small in the liquid region, but as soon as it's evaporated, it increases suddenly. So in these problems, previous problems, the methods developed and explained that we had seen yesterday, they have been applied. But important thing is that these methods should be very robust. In general, if we just develop these methods and use certain equations, it may not work in all the situations. It has to be tuned, the parameters to be tuned, and the source terms should be added in an appropriate manner so that we can get a converged solution. For example, what we normally talk about, source term linearization and so on, they have to be done properly and appropriately to get a converged solution. We will see next. We will see some other case studies which involve heat transfer. Some of these we have gone through yesterday. It's a supercritical flow. It is important in the case of nuclear power plants. Many times the water or the coolant goes through loops, and which gets heated and gets into supercritical state. So the state of water may go from highly incompressible, nearly incompressible, to the supercritical state. So the as we have seen yesterday, in the case of carbon dioxide dispersion or discharge, in the case of carbon dioxide capture and the sequestration problem, I have mentioned that when the fluid gets into a supercritical state, the main problem is that the properties, thermodynamic properties, such as specific heat and density, they can change rapidly within a short period of temperature, short range of temperature. For example, in the graph here at the bottom right, we can see that the specific heat goes to a value of 70, that is increases 7 times, and the temperature is between 650 degrees centigrade to 700. So normally when we do simulations, we use various equations for specific heat. We assume that it is a function of temperature, but those equations may not be valid here. This variation has to be captured accurately. So the property calculation is very important. So we have used the lookup tables for density and specific heat as a function of temperature. Not only this, the transport properties like viscosity and thermal conductivity also vary in the same manner. But normally these used lookup tables are computationally very expensive. So there are various techniques, many equations are derived for different scenarios, etc. So knowledge of these are essential to model a supercritical flow accurately and within practical time or reasonable time. So another aspect with another problem which involves heat transfer is the proton beam heating. The various particles come out and pass through various components in the nuclear power plant, and they can interact with the flowing liquid, and they can lead to heating. So these problems are to be handled with the various heat generation models for these interactions. And we have seen yesterday in fluid structure interactions a lot of problems. All of them like vortex-induced vibration or seismic activities and their influence on partially filled tanks and so on. These are all from the nuclear industry. These are all problems which occur in nuclear industry. Next problem, which we will see some case studies on hydrogen safety. It is a major issue. We will see why it is a major issue in nuclear power plants. As we have seen in the beginning of the loss of coolant in accident in nuclear reactors, this leads to hydrogen generation and its release into the containment and its dispersion and possible explosion. So this explosion of hydrogen air mixture in the presence of condensed H2 can cause structural failure or integrity of other components. So a lot of studies are done regarding storage and handling of hydrogen, and various methods are derived and designed. And it is important not only to nuclear reactors. Now there is a big thrust to hydrogen economy. So there are going to be a lot of installations which use hydrogen, and also hydrogen is a byproduct of electrolysis, fuel cells, batteries, which are going to be installed in enclosed spaces. So this is the hydrogen management is a very important issue, which has a lot of interest in this. So normally the dispersion of hydrogen it's highly sensitive to the natural convection because it's a very light gas. So all the models that used like turbulence models, right, showed able to capture these buoyancy effects. Then normally these studies also require various models for combustion of hydrogen and whether this combustion will accelerate into explosion and or detonation. And as we will see, some of the case studies, this also will include the surface chemical reactions, and as we have already seen, it will also involve conjugate heat transfer and radiation. Some of the studies, one of the areas that we had worked was on a mitigation device called passive photocatalytic recombiner. We will see details of this in a few minutes. But before that, we will see the consequence of in case of explosion and how can it be, whether it can be modeled accurately, and how the process of validation goes through that. The tie vessel, which we saw in the introductory part, that can also be used for conducting experiments involving explosion of hydrogen. So the picture here on the right hand side bottom of the animation shows the result of such a simulation. So in this vessel, the hydrogen is filled at a certain concentration, like 8% by volume, which is within the flammable limits of hydrogen, and then it is ignited at the bottom, and this animation shows the flame propagation. So these the overpressures, that is the rise in pressure at various points, are measured and are available, and the results of simulation can be compared. With this, we can see that with these models, like mostly be model, like it's a model for turbulent combustion. In the case of combustion, in the case of explosion, the process is going to be highly turbulent, and the use of turbulent combustion models are very important. And at the same time, if the one challenge while modeling combustion is, in this scenario, is, which is different from the normally combustion is extensively used in simulating the flows inside combustion chambers of gas turbine engines or IC engines and in various places. The one difference from those simulations and this kind of simulation is that here the total domain size is huge, so 9-meter long vessel, whereas and the flame has to pass through this whole region. But if you look at the flame itself, typically the flame thickness is of 1 millimeter. If you look at the flame of a candle, the thickness of the flame is only 1 millimeter. The flame is not what you see out from outside, but the flame is only the region where the chemical reaction is taking place. So if we are able to cut through the candle flame, you will see that it's actually hollow, and the flame, that is where the reaction is taking place and the heat is released, is only less than 1 millimeter, or in the flames in a gas stove. Now we need to model that to correctly capture the temperature and the pressure and so on. And at the same time, the whole process has to be captured in the whole domain. The difficulty is that if you try to refine this, if you try to create a mesh, a computational mesh for these kind of domains, a rule of thumb says that you need at least 10 to 20 elements within a flame. So you can imagine, you can calculate the number of elements required in case we have to to create a mesh where the mesh size is of the order of 1 millimeter per kind of domain. And even if you use some sort of adaptive meshing techniques, still there are difficulties because we can see the flame here. It is actually widely spread. It is not restricted to a thin fan, especially in turbulence. The flame can be, things can take place in various places with this model. So certain special methods are required. The models were modified to get accurate results with the post mesh. So this development was done by Dr. Chandil, who explained to you various turbulence models. And these are validated against various experimental data like this. And then after this, this was used in many actual installations, because this is one thing which cannot be actually tested in an existing installation. So the only way to analyze the effect of different scenarios is to do the simulations. So this model was used in the analysis. Then we will see some of the case studies related to hydrogen management. I mentioned about hydrogen recombiners. If you recall the Fukushima accident, this year is the 10th anniversary of that accident. There was an earthquake, I think and then there was tsunami, and there were explosions found in one of the buildings, reactor buildings. There were 4 buildings, and we can see there was an explosion in one of them. The later investigations pointed to the fact that there could have been leak of hydrogen and its entrapment and accumulation, and that its ignition might have caused this explosion. So after this, a lot of attention was paid to the hydrogen removal systems in nuclear power plants. One method or one device suggested is the hydrogen combiner. The merit or peculiarity of this device is that it is a passive device. That means it doesn't need any electricity to operate or any other energy source. It can work by its own characteristics. So it is advantageous in the sense that one first casualty of an accident in a nuclear power plant could be the electrical energy cutoff, like in a station blackout. So a passive device is also more reliable compared to any other device which may depend on ventilation system, which may depend on the external power. Fluidyne worked with BARC to design and validate such designs. BARC is really involved in this aspect, and we have helped them in developing, validating, and formulating a procedure to simulate and optimize these devices. So these are used to remove hydrogen. I'll briefly explain. This device is very simple. It is nothing but a row of steel plates, maybe 1 mm thick, 2 mm thick steel plates, which are separated by a few mm. So it's a row of plates, maybe 50 or 100 plates with the gaps, small gaps between them. And these steel plates are coated with platinum. So what happens is, if this is placed in a hydrogen environment, hydrogen diffuses into the space between the plates. And the ignition temperature of hydrogen, the auto ignition temperature of hydrogen is very high under normal circumstances. It is about 500 Kelvin, more than that. So in a normal room conditions, hydrogen will not get ignited by itself. It needs a source, like a spark from electrical switch. But when a platinum plated steel plate is placed in hydrogen oxygen environment, this platinum acts as a catalyst, and hydrogen combines with oxygen by itself without any external energy addition. But in contrast to normal gaseous hydrogen-oxygen reaction, normal hydrogen gaseous reaction is highly exothermic. That is why they are used in cryogenic engines. It's highly exothermic, and it releases a lot of heat, and it's very fast. If you look at the speed, flame speed, typical hydrogen laminar flame speed is, hydrogen air flame speed is 4 meter per second, which is actually 10 times that of methane air flame speed. So you can say that, like a natural gas, compared to natural gas, hydrogen is 10 times, an order of magnitude more reactive. With the hydrogen oxygen, the flame speeds can go at much higher values, like 10 meters per second. But that is when it is ignited with a spark plug and it burns in the atmosphere. But in the presence of a catalyst like this, like platinum, it burns slowly, very slowly. So this slow reaction, this is still exothermic reaction, heat is released, but the rate is very slow. And what happens is that this slow reaction here, for example, this picture shows a schematic. There are plates with a gap between them, and it is immersed in the hydrogen environment. Hydrogen slowly diffuses into the gaps, and it reacts slowly, generates heat. Now the temperature increases. So the increased temperature causes natural convection. So a natural convection starts setting in. It takes in, it sucks in more hydrogen oxygen mixture into the gaps between the plates. So the reacted mixture goes up through the top, and the fresh mixture comes in. So slowly the whole hydrogen in the domain where this device is placed gets consumed. So that is why this is called a passive reactor. It doesn't need any external power to operate. As soon as it finds hydrogen, it starts sucking it in and starts burning. Now, its design poses certain challenges. Even though the rate is slow, the reaction is still exothermic. Still heat is released. So the design should be such that this heat release should not increase the temperature beyond the auto-ignition temperature of hydrogen. If that happens, it can ignite the remaining hydrogen-oxygen mixture. So in that case, a solution to a problem will cause much bigger problem, because this heated plate can act as a very large heat source and ignition source, and it can lead to detonation. Otherwise, it would have only exploded, but in this case, it can even detonate. But there is another thing. This at the same time, the gaps between the plates. If you look at the gaps between the plates, they cannot be too wide, because if it's too wide, then the reaction rate will be the removal rate will be low. If it is too slow, then the frictional losses will be high, and again there will be a decrease in the removal rate. So the design of this device, even though it looks very simple, is a bit complicated. You have to consider a lot of factors into this. So it is difficult to do experiment. It is really possible. Experiments are done, but it's time consuming. So BARC, along with Fluid, and developed these models for this. If you look at the so here, in addition to the heat transfer, there is a reaction at the surface. So the hydrogen and oxygen reacts at the surface, and that heat is released at the surface. So first it goes to the plate, and then it is converted back into the fluid flowing, with hydrogen air mixture. And at the same time, there is a radiation also. So if you look at all the processes, there is a fluid flow through the plates. So here, this picture shows catalyst plates. This is the surface with catalyst on it. So there is flow through the gap between these plates. There is reaction at the surface, and then there is heat conduction inside the plate. There is a radiation between the plates, and the radiation between the plates and the surrounding structures, and so on. So in the model that we built, we used the finite volume method for the fluid flow, and the chemical reaction was modeled using a surface reaction module at the surface, which releases heat at the surface, and then heat conduction in the structure is modeled using finite element method. And this is a transient problem, and we need to get time accurate solution, because it is also important how much time it takes for this recombiner to remove the oxygen. These three solvers were coupled in an appropriate manner. So this shows the result here with the two plates. So this domain shows two plates. So you can see the temperature plot. The hydrogen volume fraction is highest at the outlet at the entry. So the reaction rate is the highest there, and the heat release rate is highest, and the temperatures are also high there. And slowly it gets cool, and gets dissipated in the whole gas. Similarly, see the hydrogen concentration. This picture shows the hydrogen concentration. Hydrogen-rich mixture. What I mean by the hydrogen-rich mixture, in the hydrogen-air mixture with the ambient concentration comes at the bottom, denses, and the hydrogen gets reacted at the surface. As the hydrogen gets reacted and depleted at the surface, the hydrogen from the sender diffuses onto the plate, and that also gets converted. So as you can see that the hydrogen concentration in different plates are not the same. There are side effects, etc. So the problem has to be solved. We cannot use the symmetric conditions everywhere. So that has to be judiciously selected. Again, in the literature, experimental data are available for certain, like for any other nuclear applications, application of simulation nuclear industry. First, it has to go through a thorough evaluation process. For the recombiners, also there are standard benchmark experimental data available. So first, the model was tested against them, and BARC used it in their own systems. So here, what is shown is a large containment, large room, and the recombiner is placed at the center, and the whole region is filled with hydrogen air mixture. So on the right hand picture, the animation, it shows we can see the recombiner plates here. And as it starts working, the divisor is hydrogen, and immediately the hydrogen within the recombiner is consumed, and it moves up, pushing the hydrogen at the top, hydrogen air mixture at the top, and also slowly it draws the hydrogen mixture with the hydrogen and air from the bottom. Eventually, the whole domain, the hydrogen from the whole domain is removed. That is why we see after some time the mixture with less concentration in hydrogen is coming in.
Anil, if I may add one sentence for this particular slide.
Sorry?
If you permit me, I would just want to add 2 sentences on this slide.
Oh. Yeah, please go ahead.
Actually, the room you can see, it is only quarter. We have simulated only 1 quarter symmetry. And the recombiner box actually is the smallest one that you see there, the dark black one. That is the recombiner box, not the big one.
Yes, this is at the center.
Box. So we made this mesh because the recombiner, the plates are modeled, and the plate thickness, as Anil told, it ranges only a few millimeters, whereas the vessel size is very large. So we need actually a graded mesh to capture what is happening inside the recombiner and the coarse mesh outside. So this coarsening actually we did over several levels. That is why you see several layered boxes there. So the mesh becomes gradually refined in each of those boxes. Thank you.
Okay, thank you. And further, these models were validated against various other benchmarks, because now this particular model is used in various countries, not just in India. You can see the effect of placing hydrogen recombiner in an environment with hydrogen. The temperatures are high and it gets distributed. Now, in one of the earlier slides, I mentioned about the importance of designing it properly, such that the recombiner does not cause a problem by itself. So one of the constraints was that the plate temperature should not exceed the autoignition temperature of the hydrogen. This study illustrates that effect. So here what is seen is a volume with a recombiner in that, and still we can see that hydrogen is consumed and the temperature increases. So what you are seeing here is the increase in temperature. So you can see that the energy release is taking place only at the location of the recombiner. Everywhere else the temperature is well within the limit. It is less than the ignition temperature of hydrogen air mixture. This is with one design, and with another design, you can see that it can actually lead to burning of the incoming hydrogen jet. See, the recombiner is at the middle, but now we can see that its operation of the recombiner actually caused the ignition of the hydrogen jet coming from the bottom and causing a fire. So the design optimization is very critical in this. The hydrogen has to be removed at as fast as possible, but at the same time, the rise in temperature should be as low as possible. We can see the details of this in these 2 publications by scientists from BARC. on the development and the validation of CFD model for catalytic recombiner against experimental results. These are available in the public domain. Now we will look at other mitigation strategy and some issues related to fire and dispersion of hazardous gases. One such important component in a nuclear power plant is a fire door. A nuclear power plant contains thousands of doors. Could typically contain many levels of building on the underground, and thousands of doors. And each of these doors are designed to withstand all the foreseeable accidents or natural calamities, such as earthquake. These are designed to withstand earthquakes, an explosion wave from an explosion outside, or even an aircraft crash into the building, into the reactor, into the plant. And these are special kind of doors, so they are multi-layered. In addition to this, these doors also should withstand the fire for very long times, maybe 2 to 3 hours. Fires at different levels. And in addition to that, these also should be leak-proof. There are certain limits to the allowed leak through the gaps between the doors and between the door and the frame from one room to the other when the doors are closed. For example, with a pressure difference of 200 Pascal between them, between two sides, the leak should be less than a meter cube per day. So the leaks used, the seals used for these doors should be very good. So all these things are considered while designing a door, a fire door for nuclear power plant. Now, what happens is that once these are installed, and this particular study which we had conducted was necessitated because certain changes had to be made. Because the doors, the plant is already commissioned and the facility is already operating and the door is already installed. But after that, there were certain changes in the adjoining rooms. That is another aspect. When the fire load in case of an accident, that is evaluated based on the sources of possible fire in possible sources of fire in the rooms. So if a new equipment comes into a particular region, then its effect on all the neighboring security or safety systems are to be immediately considered. So in this particular case, in this plant, it was found that certain additions to the electrical wirings and other equipments necessitated a modification of the fire levels and hence redesigning or making some changes to the original design. And to save time and avoid various difficulties, the first simulation was done to optimize these design changes and to see whether these changes, the proposed changes, can actually fulfill the requirements with respect to the changes. So as you can see, this door, these are multi-layered and there are a lot of hinges and other things specially designed. Then there are seals. So there are heat sources. Heat sources needs to be modeled in the domain. And then the response of the doors in terms of both temperatures and stresses in the door elements. So the criteria is that the door should maintain its function during the fire. The door should not collapse. and there should not be any deformation of the door. That seal should work even in the case of fire. Actually, the seal should close any existing gaps and prevent the smoke from escaping from one region to the other, and so on. There are certain standards of heat fluxes to be considered, which are calculated based on the potential sources. So, and there are certain limits on the door temperature when it is exposed to the fire, like it should, maximum temperature should be lower than 180 degrees centigrade. So this domain contains electrical equipments and many boxes, the ventilation devices, the zone of the fire, and then some other domains and so on. Various doors, open doors, and the doors themselves can burn and generate secondary fires and so on. So this project involved creation of geometry, selecting parameters for calculation and various other data, and modeling the ventilation, adaptive ventilations, and the fire simulation up to 90 minutes. And this simulation should included fire, modeling of fire as well as the structural response to it. So normally the fire data is given in terms of fire curves, which gives the time variation of the heat load. So during the modeling, the ventilation was also considered. So you can see the various streamlines were obtained, and the transient temperature spread through the doors, and on the door temperature itself and its deformation and the stresses on various components like the frames or each panel, and the insulation between various support. Support is also important because the deformation of support is also important, because one criteria is that the door should not fail in case of fire. So you can see the more details about this study. We have presented one paper in Athens conference 3 years back. I will just briefly introduce two more other aspects related to the nuclear industries, and where the simulations are being increasingly used in the near past. And then we are closely associated with various organizations across the world, both in India and Europe, in developing models for these processes. Such thing is the radon release and its effects on the people and its dispersion. So you know the radon is a radionuclide, and it's a gas. It comes from various sources like underground water or from the walls and from various materials. Radon decays into its various other radionuclides, like for example, radon decays into polonium-218 with a half-life period of 3.8 days, then further goes to lead-214 and so on. There's a chain of these decay process. So all of them up to say polonium, lead-218, lead-214, bismuth-214, etc. They all emit, as you can see, alpha particles and beta particles, which when are ingested by human beings they can cause cancer. For example, if we inhale radon, the radon itself doesn't cause a problem because it will be exhaled, because it is a gas. But the issue is with the decay products. They don't get exhaled. They get formed inside our body and they get attached to the lungs, just like the virus causing COVID-19. And this can cause in the long time lung cancer or various other medical health issues. So the nuclear agencies, our scientists in our nuclear agencies are involved in developing models and conducting studies on the various aspects of transport of radioactive nuclides and their interaction with all the existing dust particles and so on. And this has nothing to do with the nuclear reactor. nuclear power plant, even in the normal ambient, normal environment, these things occur. Because a few years back there was a news, say for example in Bangalore, where I am from, the water is taken by very, very deep wells, and they measured higher levels of radon emission from that. So these, so a lot of simulations are being done to analyze the effect of ventilations, effects of ventilation on the radon concentration in confinements and in rooms. For example, say for example this problem, which involves a two-room building with one door as an inlet. There is an inlet, and then air comes through the door and it escapes through the window, and then there is a partition. So if you look at the flow field, if the air comes in through the door, there is an outflow through this window, and the window in the other door is closed. So you can see that there is a lot of flow in the first room, but there is not much of a flow in the second room. So there is a sort of recirculation zone in the second room. So if you look at, if you simulate the flow of radon along with this, you can see that in the second room, the lead concentration, that is a product of decay of radon, is much more because there is less ventilation. So we can see the details of such previous studies. In many such studies were conducted by scientists in India, people working in India in this field using fluidine ventilation software. So another aspect which is of importance and which we are currently working with the BRC is the attachment of radionuclides onto aerosols. Let me briefly introduce this process. So in the normal air, there are air molecules. So this picture shows, I'm not showing the air, the white color is the background air. And then there can be radon or thoron molecules. The typical diameter of molecule is about 0.2 nanometer, 1/5 of a nanometer. So they are there and they get decayed according to the chain, the decay chain that we have shown. So the decay products, that is polonium or lead or bismuth, etc., they have a property. The radon gas molecule doesn't get attached to any surfaces. It remains in the air. But the decay product, they can get attached to any nucleus or any themselves and form bigger clusters. So you can see that multiple product molecules, they get attached to each other and forms a big clusters, the size of which is about 1 nanometer, an order of magnitude more than that of the radon molecules. Now the problem with this is that these things then can get attached to aerosols. We might have seen about 10 ppm, 10 pm, PM10, PM2.5, etc. These are size of the aerosol. So aerosol size varies typically from 10 nanometer to 10 microns. So the smallest size of aerosol is an order of magnitude larger than the cluster radionuclide product cluster. So they can get attached to that. So if you look at this, the aerosols gets transported through air in a different way because they are heavier. They get settled onto the floor. You can see in your room, they get deposited on the floor. So along with this attached radionuclides also will get deposited. And there will be some part of the radionuclide, the decay products in the air itself. So normally these the part which remains in the air free, that is, they are not attached to the aerosols, is called a fine fraction. That is a term used in the community. And the fraction which is attached to the aerosol is called a coarse fraction. So the dispersion, the transport of this material in the air, surrounding air, is different because the aerosols are heavier. They can get settled very quickly. whereas the fine fraction is on the size of only 1 nanometer, and they may freely flow through the air. So this part is being studied extensively by now. We have developed softwares. Now it is in the validation and testing stage. And these, you can see that these problems involve 3D unsteady simulations and convection, Brownian diffusion of small particles, then turbulent diffusion, and deposition on the walls, various walls, horizontal walls or ground, the floors, or any other surfaces like table surfaces or human body, or they can be inhaled by human beings on the plants. And we have to model the attachment of the decay products onto the aerosol. And once these are on the aerosols, again they decay. So decaying is like the living particle, alpha particle. So it is like shooting your gun, and there is a recoil of that, and then the decayed product can get detached. It's called detachment due to recoil. So a lot of processes are there. These are to be these can be considered in our model. We have considered all these things. We have developed an Eulerian model to model the transport of aerosols and the decay product transport. These are modified with various source terms and so on. And the calculations are done. For example, if you do the calculation of decay product, this shows, say, if we start with the simulation at 0 seconds and after 100 seconds, you see that initially there is only radon. The fraction is nearly 1. And after 100 seconds, if there is no, you can see that decay products are formed without any aerosols. You can see, for example, if you take polonium-218, after 100 seconds, the value of polonium-218 is 1.8 into 10⁻⁴ without any aerosol. But with the aerosol, you can see that the fine fraction, that is, which are free to move in the air, is only 2 into 10⁻⁵. All the remaining part, it is attached to the aerosol. So 80%, 90%, nearly 90% of the fine fraction gets attached to the aerosols. And we will, I will finish this presentation with just one more problem that we have solved, which is on the nuclear waste disposal. And it is a very important aspect of the nuclear industry. The spent fuel has to be disposed of in a very careful manner with a lot of precautions to avoid damage to the environment. So normally what is being done is big tunnels are made in underground or in mountains, and they are kept, these capsules containing nuclear waste are kept in such tunnels. So this picture shows one such containment disposal site. Contains a main tunnel, and there are side tunnels going through that. So you can see these tunnels are of the size of half a meter, and this big tunnel is maybe a few meters. And there is ventilation. These are ventilated. And most important part is that these are immersed. These are below the ground, maybe 100 meter or more than 100 meter or 500 meter below the ground level. So in this case, and these are to be kept for many hundreds of years. So if you look at the flow, these kind of systems, it involves tunnels. There is these are surrounded by soil, and in the soil there could be water. It could be saturated with water. So if you look at the flow here, there could be flow from the seepage of water into these tunnels. Even the seepage rates are very small. On a day, a per day basis, these are going to be kept there for thousands of years. So normally, before designing and installing such commissioning a site, the studies are done, simulations are done for 300 years or 30,000 years and so on. Very large, very long time scales. By considering all these physics to see that whether there are any chances of the failure. So these problems typically involve, there is a heat source because the nuclear waste is actually a heat source. It can still release heat for hundreds of years. And so you can see that that waste is surrounded by it is put in a steel protection pipe kind of thing, very thick steel pipe. And then there is a gap between the steel and the surrounding rock or soil. So what happens is that the rock or soil is saturated. Then the heat from this the source, it can cause evaporation of the water. Then there could be water seepage into this steel onto the steel protection, and the steel can get corroded, and the corrosion of steel can produce hydrogen, and the hydrogen can the pressure can increase inside this due to the hydrogen production and the heat release, and this hydrogen can get into the soil, which can again increase the pressure there. So all these processes are model. And this basically this involves flows in unsaturated soils. It flows through porous media, and it is a two-phase flow. So the capillary action has to be taken, has to be considered. Then there are thermal problem, and there is ventilations in the gallery, and so on. So the one challenge is, as I mentioned, different time scales. The analysis has to be done for thousands of years, whereas the process, a seepage of water, it has a time scale of a few seconds or a few minutes. So different types of methods in this analysis, different types of methods suitable for each process were identified, and individuals, and they were coupled properly to study the whole problem. So this basically involved the solving continuity, momentum, energy, and species for each of the phases separately, and all these things are the flow has to be considered. Flow and diffusion are to be considered through the porous media. So there are different models for such things, which are different from the models normally used for gaseous diffusion and so on. So these are typical mesh used. We can see at the center that the domain contains that at the center we can see the tunnels, and then the domain size is about 100 meters on each side to consider the effect of the soil, the flow through the soil. So this shows the temperature variation for a span of 300 years, slowly increases. And here you can see in 300 years, initially the temperature increase is large because that nuclear waste is releasing heat at higher rate. But as it decays, the heat release from the nuclear waste decreases. So as we can see, after a few years, that heat release rate decreases and the temperature start decreasing because the temperature is absorbed and dissipated through the soil. So various quantities are assigned. Also, we estimate how much seepage occurs into the gaps between the steel protection and the rock. And the red color here shows the development or filling of the gaps with water. Find that in about 100 years, the half of the gap is filled with water. So the complexity or the challenge to model this is that if you try to model water seeping and into such small gaps, you'll find that you have to use very small time steps, a few less than a second. But as you know, we had to do the simulation for many hundreds of years, so we use the subcycling, proper subcycling between and coupling between the different methods. So I'd like to say that these kind of problems nowadays, such complex problems involving multiple physics, can be handled by intelligent coupling of various schemes and methods to a satisfactory, to get reasonable results. And this problem, as I mentioned, there were three parts, one without hydrogen injection, and after some time there is a release of hydrogen, and it can occur up to 4,000 years. So these installations, before commissioning them, they have to undergo such thorough studies for 30,000 years or 1 lakh years and so on. Very long time scales. So the hydrogen injection completely changes the water filling behavior inside the cavities. This picture shows the evolution of hydrogen and its dissipation. It's a very slow process. It takes many years, but still it has to be calculated and make sure that nothing is going to happen for the near future or even long time future. So with this, I conclude this presentation. And there are some other aspects which some other studies we have done on the effect of modeling, the effect of nuclear power plants in the environment, neighboring environment, for example, visibility or dispersion of radionuclides released accidentally from the plants, the near region, etc. So this will be covered in session tomorrow. Similar studies will be covered in a session tomorrow, but you can see some results here. These simulations are done in a large length scales, spanning kilometers, a few kilometers, starting from by modeling the process near the nuclear power plant very accurately. Thank you for your attention, and we can have a discussion if there are any questions.
Thank you, sir. Hello, everyone, sir. I think there are some doubts that are posed here. Yeah, 1 minute, sir. Just.
Is there any unanswered?
Arunmurthy sir answered one question, I think. Let me see. Okay.
Mr. Sonavane asked about iodine. How come
Yes.
is there in the nuclear reactor? So Anil, if you would like to comment on that. So I just told him that iodine isotopes actually form as part of the fission decay chain, and they do pose a health hazard for the people around when they are released into the atmosphere. So normally NPPs they supply iodine tablets actually to people residing around the nuclear power plants. It's a common practice everywhere, so that they don't develop thyroid problems.
Yes, I know only this much, and it is used to neutralize the.
Yeah, radioisotopes. Yes.
I mean, frankly, I am not an expert in nuclear engineering, as it. Is there any?
So I think Arunmurthy sir answered most of the questions.
The second one by the same gentleman, if there is an alternative to uranium nuclear plants.
Yeah. Fast breeder reactors. We are trying to use a thorium.
Yeah.
Fast breeder reactors. Yes. It is still
Also,
it is still not yet commissioned. It is still
yeah. If you can call ITER as a nuclear reactor, that is a new thing developing.
Yes. We use helium or tritium.
Sir, actually, I have one doubt.
Yes.
The current prototype fast breeder reactor that was being constructed in India, it is using liquid sodium as a coolant. I mean, like as a heat transport kind of thing.
Yes.
We can model such kind of things also, right, sir?
Yes, yes. Actually, we have done a project with IGCA.
Okay, sir.
One important thing there is that sodium, the bubbles, there could be bubbles, sodium, which may move from one side to the other part of the liquid. I have shown one animation yesterday of bubble movement.
Yes.
Actually, that was done as part of a project for IGCA. It is actually a sodium bubble.
Okay.
Yes. So we can model the flow of sodium.
I think we can even model the safety considerations also, like leaks of sodium. That is very important also.
Yes, yes. We can. There can be modeled.
Raghavendra Upadhyay, sir. Dr. Raghavendra Upadhyay. I have unmuted you, sir. You can ask your question.
Yes, sir. Actually, I'm not asking any question, but just want to add, because my PhD is related to this nuclear.
Yes.
That actually new technology, which is the supercritical technology nowadays used in the power plant. And this supercritical technology, when coupled with this nuclear technology, then many the questions which generally generated here automatically get cancelled, will lose its relevance, because the technology itself solve many problems. As far as fuel is concerned, we can answer like that. We are having so many fuels, even biodiesels and all, but still we are going with petrol and diesels. So having fuel is not enough the thing, but to prepare that ore or the raw material of that fuel for the suitability of the reactor is a big challenge. So many countries or many powers having other fuels also, but their preparedness need a lot of things, and the cost estimation is also there. So that's why generally we are here dealing with two-phase fluid, but yesterday also someone saying about the supercritical technology, where there is simply a fluid. There is not much detention between the liquid and the gaseous phase. And modeling it is a very easy task as compared to two-phase flow. So I think this thing actually I want to add only. Thank you. Thank you.
Yes, you are right. But still, there are many power plants coming up with the existing technologies, and they need to be monitored, and their modifications are to be analyzed. And then supercritical flow, yes, it is simpler in the sense that there is no interface involved. The only difficulty in modeling supercritical flow is properly capturing the property variations when the flow gets into the pseudocritical point. And that is a very important point. Actually, that is one hurdle many people have tried to address in the recent past. There are a lot of literature on that, how to model the property variation in the supercritical region. If you look at the literature on the modeling of cryogenic engines, you can especially see that. And this space vehicle technology is also going for a higher pressure engines for more thrust. So higher pressure means there will be supercritical flow there, and transcritical flow. So yes, there will be new technologies which will make the current system obsolete, it is good.
Sir, one more question has come up, sir. Can we, this is from Ram Mohan Gupta. He is asking, can we simulate nanofluid concentration problem with heat transfer in Fluiddyne software? Shall I repeat it, sir?
Is a nanofluid.
Nanofluid concentration problem with heat transfer.
Could you please briefly describe what the problem is? I mean, is it a rarefied flow, or is it flow involving length scales, very small length scales?
I think it is basically a fluid with nanoparticles.
Okay, we can do that. If it is a flow with nanoparticles, we are developing this aerosol module. Aerosols are not nanoparticles; they go to 10 nanometer. But those the decay products which I mentioned, clusters, they are of the size of 1 nanometer. So we are slowly we have included some models for their transport, including their dispersion, their response to turbulence, Brownian diffusion, their attachment to the walls, their interaction with the surrounding other particles, and so on. Yes, if it is a flow of nanoparticles, then yes.
Okay, sir.
And we also added many. We are also adding like a coagulation of particles or effect of temperature gradient called thermophoresis on the transport of these particles, or electrophoresis. So these models are also being added.
Sir, we are having some hands-on on this situation, sir. Nanoparticles.
I couldn't hear you. Sorry. Please.
Sir, I want to know that we are having some lectures on these nanoparticles.
No, I don't think they are being covered actually, but maybe we can share some documents with you.
Oh, yeah, okay. Examples for nanoparticles.
Yes.
Yeah. Actually, these.
Please, Anil.
Yes, actually, these I did not show those results because we have been working on those results are still getting prepared for publication or getting submitted for publication. So we will communicate to you as soon as we get through that. Yeah. Otherwise, we can, if you have any specific problem, we can actually demonstrate that problem.
There is one PhD actually coming up actually on these models. That is why I think it will be difficult to share some results, but some results can be shared. What is already published, I think we can share.
Yes, thank you, sir.
Yeah, it is.
Hello, sir.
I don't think I can share it now because it is, as I said, it is under revision process by various processes. There is one question from Dr. Muhammad.
Yes,
Does behavior of liquid metal coolants considered Newtonian or non-Newtonian flow?
Hello, sir.
Is, yes.
May I ask you one question, sir?
Yes, sir.
Yes,
yes, please.
Sir, suppose I want to use this CFD in abrasive flow machining or the magnetic abrasive polishing machining process. Can we use, sir?
Sorry, magnetic averaging?
Abrasive flow machining or the and as well as the abrasive flow machining. Can we use this for the nuclear reactor? If you want to produce manufacture the nuclear reactor barrel, and we can suppose the manufacturing by using this abrasive flow machining. Can we use the CFD software for such types of this process?
Yes, we can use that, but some models are to be used for the surface aberration. There are various models, models for the aberration of the surface, or erosion of the surface based on the local flow field. Along with that, we can use that.
But suppose again magnetic here already you have said that this software is used for the only for the flow machining. But can we use for this magnetic flow machining, sir? Or the ferrodynamic machining, sir?
This this flow solver is coupled with electromagnetic solver, so we can consider the flow coupled with the magnetic fields as well.
I think in tomorrow's lecture,
Tomorrow, I will show some examples of this.
Yes, sir.
Case studies of flow influence induced by magnetic fields.
Yeah, liquid metals especially.
Yes, sir. Thank you, sir.
Yeah. Actually, whether the flow is Newtonian or non-Newtonian, it depends on the viscosity depends on the strain rate. So the liquid metals, I have not worked on that. I need to check which properties are used. But if it is non-Newtonian, it can be considered.
I think it would depend on temperature. For example, even if you take lead or some material, above certain material, it will behave more or less like Newtonian.
Yes.
In some temperature range, it could be non-Newtonian.
Another thing is it is a single phase material. So normally the non-Newtonian fluid will have non-Newtonian behavior results from like materials like slurries or other things.
I think such problems should be modeled with variations of viscosity with temperature graphs being given.
No, it is not just the variation of viscosity with temperature. Yeah, that is normal. Here, the difference is that Newton's law of viscosity, we assume that viscosity is not a function of strain rate, that is velocity gradient.
Yes, a velocity gradient. Yes.
Whereas in the case of non-Newtonian, many fluids, the viscosity depends on the local velocity gradient.
Yeah.
So the core near the wall there will be low viscosity, and at the center there will be the viscosity will be higher.
Yeah.
Kind of thing. So that is the difference. So that is why the fluids are called non-Newtonian.
Okay, sir. I think the questions are over. I think we will end this here, sir. Anyone else has any questions?
Okay, I'm sorry that I did not use the mouse for some time, and I think my explanations now are not clear. Dr. K.V. Sidaram pointed that out. I'm sorry for that. Yes.
Okay, sir. Thank you, sir, for this very precise and relevant presentation. I think many of us here have a very good understanding right now. We'll take a break here, and we'll reconvene again after the short break at 11:15 a.m. Thank you very much. Thank you.
Thank you.
Thank you, sir.